For the first time, astronomers have been able to directly follow the motion of an exoplanet as it moves to the other side of its host star. The planet has the smallest orbit of all directly imaged exoplanets so far, lying as close to its host star as Saturn is to the Sun. This discovery proves that gas giant planets can form in only a few million years, a short time in cosmic terms.
Hello and welcome to the ESOcast. In this episode, we'll talk about the planet around the star Beta Pictoris. This star has not quite twice the mass of the Sun, and it's about 12 million years old. Although this sounds like a lot, it's actually a really young star. For example, the Sun is already about 4.7 billion years old. Beta Pictoris is one of the best-known examples of a star surrounded by a so-called dusty debris disk. Now, the debris in this disk comes from collisions among larger bodies, such as planetary embryos or asteroids. Earlier observations had already shown that this debris disk is actually warped and that there are comets falling onto the star. Now, these are telltale signs that strongly suggest the presence of a massive planet in orbit around the star. Now, with the new observations obtained with ESO's Very Large Telescope, we have definitive proof.
Because the star is so young, the planet must also have formed in only a few million years. This is good news because we already knew that disks around young stars disperse in a few million years, and astronomers were looking for proof that giant planet formation can occur within this time. The planet has a mass of about 8 Jupiter masses. It has the right mass and location to explain the observed warp in the inner parts of the disk.
The team used the NACO instrument, which is mounted on one of the 4 8.2-meter unit telescopes of ESO's Very Large Telescope, or VLT. They observed the immediate neighborhood of Beta Pictoris in 2003, 2008, and 2009. Now, the 2003 observations clearly showed a massive planet in the disk, but in 2008 and in early 2009, it had disappeared. However, in the most recent observations in late 2009, the planet has reappeared, but on the other side of the star. Clearly, in the earlier observations, the planet was hidden either in front or behind the star. So now, for the first time, we can actually see an exoplanet moving around its host star from one side to the other. This also gives the astronomers a much better estimate of the distance between the star and the planet.
Among the handful of planets already imaged, the planet around Beta Pictoris, designated Beta Pictoris b, has the smallest orbit so far. It is located between 8 and 14 Earth-Sun distances, or astronomical units, from its star. This is about the distance Saturn is from the Sun. The short period of the planet will allow astronomers to record the full orbit within the next 15 to 20 years, and further studies of Beta Pictoris b will provide the first insights into the physics and chemistry of a young giant planet's atmosphere.
Superjupiters, like Beta Pictoris b, are exceedingly rare around Sun-like stars. However, the planets found around the star's Fomalhaut, an HR 8799, together with the existence of Beta Pictoris b, seems to suggest that superjupiters may be a more frequent byproduct of the formation of stars that are more massive than the Sun. Such planets strongly disturb the disks around their stars, and that creates structures that will be easily observable with ALMA, which is a revolutionary new millimeter and submillimeter telescope that is being built right now by ESO together with international partners.
A few other exoplanets have been imaged, but they're all located farther away from their host star than Beta Pictoris b is. If located in the solar system, they would lie close to or beyond the orbit of the farthest planet, Neptune. The formation processes of these distant planets are likely to be quite different from those in our solar system and in Beta Pictoris.
The recent direct images of exoplanets illustrate the diversity of planetary systems. Among these, Beta Pictoris b is the most promising case of a planet that may have formed in a similar way as the giant planets in our own solar system.
Today, at an international exoplanet conference, the team who built the high-accuracy radial velocity planet searcher better known as HARPS, the spectrograph for ESO's 3.6-meter telescope, reports on the incredible discovery of more than 30 new exoplanets, cementing HARPS's position as the world's foremost exoplanet hunter.
Hello and welcome to the ESOcast. In this episode, we have another major exoplanet discovery coming to you from ESO's La Silla Observatory. And we're not just talking about one exoplanet, we're talking about no less than 30. It's exoplanets galore.
Including these new results, data from HARPS have led to the discovery of more than 75 exoplanets in 30 different planetary systems. In particular, thanks to its amazing precision, the search for small planets, those with a mass of a few times that of the Earth, known as super-Earths and Neptune-like planets, has been given a dramatic boost. HARPS has facilitated the discovery of 24 of the 28 planets known with masses below 20 Earth masses. As with the previously detected super-Earths, most of the new low-mass candidates reside in multi-planet systems with up to 5 planets per
In
system. 1999, ESO launched a call for opportunities to build a high-resolution, extremely precise spectrograph for the ESO 3.6-meter telescope at La Silla, Chile. Michel Mayor from the Geneva Observatory led a consortium to build HARPS, which was installed in 2003, and was soon able to measure the back and forward motions of stars by detecting small changes in a star's radial velocity, as small as 3.5 kilometers per hour, or a steady walking pace. Such a precision is crucial for the discovery of exoplanets. The radial velocity method, which detects small changes in the radial velocity of a star as it wobbles slightly under the gentle gravitational pull from an unseen exoplanet, has been the most prolific method in the search for exoplanets.
In return for building the instrument, the HARPS consortium was awarded 100 observing nights per year over a 5-year period. Now this time was used to carry out one of the most ambitious systematic searches for exoplanets so far implemented worldwide, by measuring the radial velocities of hundreds of stars that might harbor planetary systems.
The program soon proved very successful. Using HARPS, Mayor's team discovered, among others, the first super-Earth around Mu Ara, the trio of Neptunes around HD 69830, Gliese 581d, the first extrasolar planet in the habitable zone of a small star, and the lightest exoplanet ever detected around a normal star, Gliese 581e. More recently, they found a potentially lava-covered world, with density similar to that of
Observations
the
have
Earth.
given astronomers great insight into the diversity of planetary systems, and they've helped us to understand how they might form.
The HARPS consortium was very careful in their selection of targets, with several sub-programs aimed at looking for planets around solar-like stars, low-mass dwarf stars, or stars with a lower metal content than the Sun. Although it was thought that giant planets couldn't form around low-mass stars, the HARPS team has found several of them. The number of exoplanets known around low-mass stars, so-called M-dwarfs, has also dramatically increased, including new super-Earth candidates.
Although the first phase of the observing program is now officially concluded, 2 new programs have been started. And the team still expects to make many new discoveries from the first 5 years of data. There is no doubt that HARPS will continue to lead the field of exoplanet discovery, and especially pushing towards the detection of Earth-type planets. This is Dr. J signing off for the ESOcast. Join me again next time for another cosmic adventure.